Today we will talk about continuity and differentiability, which are two concepts that utilize the notion of a limit heavily. So, first of all, let's think about the word continuous and think of what does that really mean in English. Much just like the word limit, an intuitive understanding of what continuous is might provide the very first informal definition of a continuous function. Continuous in life means something that goes on without any breaks, something that does not have anything unexpected, any kind of sudden changes. A slightly more rigorous, slightly less informal definition of continuous would be to say that a small change in input results in a small change in an output. And we witness that all the time in real life. For example, when blinking. So if you're watching a bird fly by and you blink, you're not actually seeing the bird for a split second, but you expect the bird flight path to continue along a certain way because we know that birds fly continuously. So a small change in input, such as the difference in time, will produce a small change in the output, such as the bird's location. Thinking about continuous functions graphically, it actually helps to think what does it mean to be not continuous or discontinuous. So in terms of analogies here, the easiest thing to think about is a function is continuous if I can draw it without lifting a pen. So what are the functions that will force me to lift a pen when sketching them? The first example is a hole, of course, right? So I have to sketch a little piece of it, pick up my pen, and then sketch the other part. Along the same lines is a finite jump, where I draw the little piece of the function first, pick up my pen, and then continue on. There's, of course, then an infinite jump, which is a vertical asymptote in this case. Then the combination of the first two is the one case that's probably a little harder to think about. We call it a misalignment. So it's kind of like you tried patching up your hole, but you've patched it up in the wrong spot. So in order to draw the misalignment, I have to lift up my pen, draw the point in another spot, and then continue on in the other direction. Okay, so this is a very graphical description of what it means to be discontinuous. Now thinking about what does it mean for a function to then be continuous, let's try to use our practice with limits to come up with an analytic or formulaic description of a continuous function. So to be continuous, I essentially have to avoid all of these discontinuous cases. So to be continuous at a point A, or let's call it C, the function must avoid all of these above situations. So let's try to come up with a description that will make the function not be able to have a hole at C, or a finite jump, or an asymptote, or a misalignment. Okay? So how do we avoid having a hole? A hole is when the function does not even have a value at that point. So in order to avoid having a hole, we must have that f of c is defined. Okay, and this will guarantee that my function cannot have holes. Okay, then I would also like to avoid having jumps, finite or infinite. The finite jump can be described as the limit on the left is not equal to the limit on the right. Right? Infinite jump can be described as the limit at that point doesn't exist at all. It equals infinity, which is not a number, so it can be described it does not exist. So in order to avoid both types of jumps, I can simply ask that the limit of the function as x approaches c exists. Okay? And this, demanding that it exists, will then guarantee that my function has no jumps. And then finally, I would like to avoid a misalignment. And taking a look at what misalignment means, so far these two are actually satisfied, right? So this function is defined at point C, although it has a hole there. So the limit also does exist because as you come to the left of C and to the right of C, they do come toward the same point. So far we haven't ruled out misalignment. So in order to not have this, we must have that if we have a hole, then it's patched up correctly in the right spot, which will be guaranteed if the function value is equal to the limit at that point. Okay, and that's essentially saying that whatever was guaranteed to be defined by the first point and the limit whose existence was asked by the second point are actually the exact same value. So the function goes towards the point where it is in fact defined. Okay, so this will then guarantee no misalignment. Okay, so this is excellent in general, and this slide is actually quite powerful overall because look, first we started by a very verbal, very intuitive description of what continuous means. We then proceeded to describe it with a graph, and then finally ended up having a very analytic and formulaic description of it, right? So this is a verbal description of the situation. This is a graphical approach. And the most rigorous of all is this analytical description of what it means to be continuous. Okay, let's take a look at an application. So this little planktonic copepod is called Kalinas Pacificus, and it's been extensively studied, particularly its own feeding habits have been extensively studied in the 70s by Frost at the University of Washington. The copepod itself is pretty small, it's only about 3 millimeters in length, but it is a major food source for fish and whales and birds and is thought to have the largest biomass on Earth because while they're little, there's a lot of them. Now, the Kalinas Pacificus is actually a type 1 predator, which means that they will feed proportional to the amount of food present up until the point where they reach maximal feeding rate. So these points on the graph here are actual data points collected by the researchers, and they notice that 200 is where that biological switch actually occurs. Okay, so after 200, the copepod feed at around the same rate of 1250 is what they approximated. This isn't the only data they had, this is just one of the samples. But up until then, they were increasing their rate of eating as the concentration of the food was increasing as well. Okay, so they use this piecewise function to actually model the situation. Piecewise means that it's actually given in two, in this case, different pieces, dependent on the values of x. If you need practice with piecewise functions, please take a look at the pre-calculus review package. There's more resources and exercises there. Okay, so here, the first question is asking, determine the value of c here for which the limit at 200 of our function exists. So as the function is drawn now, it's continuous, right? The way that we see it now, graphically, we cannot, like what if we zoom in and there's actually a little hole? But right now it looks pretty continuous. It doesn't seem like I have to lift the pen to draw it out, right? It's asking, find the value for which this limit at 200 actually does exist. So this point of connection, that point where the behavior, the feeding behavior of the copepod switches, is where I would like to make sure that the limit actually exists. Okay? So in order to make sure the limit exists, I need to have that the limit from the left of my point of interest is equal to the limit from the right of that point. Okay? And now, the actual function is structured in very similarly the same way. So as x approaches 200 from the left, it means it's close to 200, but less than 200. So this limit corresponds to this case of the function when x is less than 200, which means that I'm going to be using this piece of my piecewise function for the formula. Okay, so this means when x is approaching 200 from the left, my function is actually cx. Whereas when it approaches 200 from the right, that means that x is bigger than 200, which then in turn means that I will be using this second piece of the function to plug in for. Okay, so here limit as x goes to 200 from the right of 1250. And now I simply have to compute those two limits and solve for c. Remember the first rule of limits, it's just to plug it in. We notice that as we plug in 200 here and there's no denominators, there's no square roots, there's nothing really funky going on with these functions, so I can straight up just plug it in. So here I will have 200c equals to 1250, and solving for c gives me 6.25, which means that 6.25 is the value for c that makes the limit at the point of 200 actually exist. This Notice that it's cx for the line. So this c is actually the slope of this line. So the slope of 6.25 means that the two lines meet exactly. If the slope here was a little higher, we would have a jump in the graph. If the slope of this original line was a little lower, we would have had a jump in the opposite direction. Okay? But the slope of 625 guarantees that that limit exists. Now, for the second part of this question, it's asking, is this function continuous everywhere? Okay? Now remember of our discussion of continuity just a minute ago, we defined what it means to be continuous at a point. To be continuous everywhere means it has to be continuous for all possible values of x. Okay? So here, this is the very first thing that we have to look at. The function is in two pieces, so let's take a look at the two pieces separately. Is the first piece continuous by itself? So is this a continuous function? Well, it's a line, and a line has no holes, no jumps, no misalignments, so it's continuous. What about this function, the second piece? Well, 1250, that's a horizontal line. Still a line, no holes, no jumps, no misalignments. So the two pieces separately are continuous. Now we just have to make sure that they connect in a continuous way. So they don't connect with a jump and they don't connect with like a weird misalignment or a hole. Okay? So the first thing you have to state though is that for all values bigger than 200 and less than 200, the function is continuous, which means that we only need to check the actual point at 200. So we need to check x equals 200. And the way we check that is based on our definition of continuity from a couple of slides ago. So in order to check that the function is continuous at some point, we actually do need to go through the motions of checking the three things that we've identified here. Okay? So let me make use of being able to copy things and put them here. These are always, these are always the things that you are going to actually check for when you're checking for continuity. Except for, I'm not checking at some point C, I'm checking, at a very, very particular point C, and that is 200. Okay, so I'm going to replace all of my occurrences of C by 200. And now I have to go through and see if these work. If one of them fails, that means the function is not continuous. But if they all work out, it means the function is continuous at the point. Okay? So, is f of 200 defined? Can I compute f of 200? So again, first I have to see where does 200 sit, and x is less than or equal to 200 here, so I'd be plugging it into this expression, which means that yes, it's defined. It's 6.25 times 200. So this, yes, it's defined. The second question asks, does the limit at 200 exist? Well, this is actually exactly what we did in the first part of this question. We found the value of c for which that limit exists. So normally this will translate into computing limit from the left, computing limit from the right, making sure that they're actually the same thing. In this case, yes, we already made sure that that holds. And then the last part says, does the function value equal to the limit? And again, we can plug things in here, right? So this will be 6.25 times 200. And the limit from the right, though, was exactly computed as the exact same number, so 1250. So yes, this also works out, which means that the function is continuous at 200, which means that it's continuous everywhere. Let's now think about the derivative of the function and when that does or does not exist. We say that a function is differentiable if the derivative exists, and we say it's not differentiable if it doesn't exist. Here is the definition of the derivative that we've come up with a couple of lectures ago. The derivative, that's just a notation, is the slope of the tangent line. That's the graphical description. It's also this limit, which is the analytical or formulaic description of it, right? Remember that this was just rise over run of a secant line as the 2 points of the secant line were coming closer and closer together. So, thinking kind of like we were thinking about the continuous functions, it's easier to think about when the derivative might not exist. Because so many things have to sort of go right for it to exist. I should be able to compute this limit. I should also be able to draw a unique tangent line in order to be able to compute its slope. So first of all, in terms of the limit, in order for the derivative to exist, this limit has to exist. Remember, what were the situations where a limit could not exist or did not exist? There were cases like when the left and the right limit were not the same, or there were cases of the asymptote, so finite jump or infinite jump. Thinking about it more graphically in terms of the tangent lines, in order for the derivative to exist, I should be able to draw a unique tangent line at the point of interest, okay? And if I cannot do that, the derivative does not exist. So please pause the video here and think about, just sketch a couple of function cases where you would not be able to draw a unique tangent line at a point, okay? Now that we've thought about it, here are some of the cases when I would not be able to draw a tangent line. And this actually takes care of all discontinuous cases as well. I cannot draw a tangent line at a hole because there's nowhere to attach the line to. I cannot draw a tangent line at a jump because I don't know which side to draw the tangent line from. Should I be following the shape of this or this? If I cannot draw a unique one, I will not be able to deterministically compute the slope. I also cannot draw a tangent line at the asymptote. As the function gets closer and closer together, this point is not even defined, so there's nowhere for me to attach the tangent line to. And misalignment is kind of the same problem as the hole, right? Where do I draw a tangent line? I cannot draw it there. There's nowhere to attach it to. And I most certainly cannot draw a tangent line at a point because it's not even clear which direction it has to point in. So all the discontinuous cases are inherited for non-existence of the derivative. But there's another one case where the function is continuous, but you cannot draw a tangent line, a unique tangent line to it. And this is what we call a cusp or corner. So here, the issue, of course, is if I draw from the left side of it, my derivative, my slopes have to be pointing in one direction. If I draw from the right side, the slopes will have to point in the opposite direction. If I cannot draw a unique one, I cannot actually compute one unique slope, which means the derivative does not exist. So these are all the cases when the function is not differentiable, described graphically. Let's now think back to our favorite copypod and ask ourselves, well, this function was shown to be continuous. Is it differentiable? Okay, so I'm not going to do this analytically. We're going to analyze it purely using the graph. So differentiable, once again, and this is going to be important throughout, is derivative exists everywhere. So derivative exists, which means that we can draw a unique tangent line at every point. So looking at the graph here, again, just like in the continuous case, I can see that the first part of the function is differentiable everywhere, right? It's just a line, so I can draw a tangent line to a line at any point. It's going to be the line itself. It's a pretty boring tangent line, but it is unique. So the slope of this line everywhere is this value for c, which we actually computed to be 6.25. So in fact, I can say definitively that the derivative all along here is equal to 6.25 because that's the slope of my tangent line. Let me note that. So here, the slope, which means the derivative, is 6.25. The slope, which means the derivative here, is always 0 because the slope of a horizontal line is 0. It doesn't rise anything, but it runs. So the slope along this portion, which is the derivative of this portion, is 0. So my only question is, what is the derivative at the point of connection? The function is continuous because we've decided that at 6.25 is exactly where they will connect at the slope 6.25, but that still doesn't mean that it's differentiable. So if I look at this point here, how am I going to draw a tangent line at that point? I cannot draw a unique tangent line at a corner, right? It's not clear how is that going to go. Is it going to follow this line? Is it going to follow this line? Is it going to be something completely different? There's no way to draw a unique tangent line there. So at that point, the function will not have a derivative. So is it differentiable everywhere? It's in fact differentiable everywhere, except for at the point of connection of these two pieces of a piecewise graph. So everywhere except at x equals 200.
Look at a few more examples of piecewise functions to discuss their continuity. So here I have the function that has two separate pieces, x plus 2 for x less than or equal than 2, and x squared for when x is bigger than 2. It is a good idea if you're able to actually draw a picture, because you will be able to get a sense of what the function looks like and where the problematic points might be better from the picture. So here we have that at 2, the function switches the formula from linear to quadratic. So I know that at x equals 2, the shape of the function is going to change. Up until the 2, so for x less than or equal than 2, the function looks like a line x plus 2. So let's sketch the line x plus 2. X plus 2 is going to be a line that will have slope 1 and y-intercept of 2. So it's going to be a line that goes like this. And because here x is allowed to be 2, I can actually plug 2 in for x to see what the y value of the function at that point is going to be. So 2 plus 2 is 4. So the point up here is actually going to be 4. Now, I'm not continuing this line past that because my line is restricted by the domain to be the actual function up until 2. After 2, for x greater than 2, my function becomes x squared. Now, you might as well draw the entire parabola and then take only the piece that you need. The one thing you're going to have to figure out is how it actually interacts with the existing function at the point where they're supposed to connect. Do we believe that they connect or do they not? So I know that this doesn't allow for x to be equal to 2 because only one of the two cases can allow for it. Otherwise, we wouldn't have an actual function. But if we think of the limit of this second piece as x approaches 2 from the right, because x is bigger than 2, what is it going to be? Remember that the first rule of limits is to plug it in. So if I plug in 2 in for x, 2 squared is going to be 4. So the parabola, in fact, will approach this point 4 as well. So I can draw my parabola here, and I know that I'm actually going to take a piece of it after 2. Okay, it doesn't look very symmetric to me, so let me just resketch it so it's at least approximately the same on both sides. There we go. Okay, so overall, the graph of my function is a line followed by a parabola piece. Okay, the dotted parts were just so that I can view the parabola in full, but only consider a piece of it that I care about. Now, if we want to discuss the continuity of the function, a graph provides a good intuitive starting point, but this is, of course, not exactly rigorous. So we have to go through the 3 steps of the analytic continuity definition in order to make sure that this function is continuous or not. So before we get onto the 3 pieces, remember that the 3 pieces actually talk about continuity at a point. Let's think about what the function looks like on most of its domain. So at the beginning, it's a line. Well, lines are continuous. There's nothing I can plug in into the equation of a line that will give me any kind of trouble. So the line piece by itself is continuous. The parabola piece by itself is also continuous, which means that our only point of concern is the connection. Do they actually truly connect there or do they not? So this is an important part of your justification. We're going to write down that since x plus 2 and x squared are themselves continuous everywhere, that means that I don't have to actually think about every single point in the domain. I only have to think about the connection point. Each of these pieces is perfectly continuous. I'm only concerned about whether or not they connect. So since they are themselves continuous, we only need to check the connection points or the connection point at x equals 2. And this is where we're going to employ our 3 parts of the continuity definition. So first of all, we need to check, does f of 2 exist? Second of all, we need to check whether or not the limit at 2 exists, which means that we're going to, well, actually, let me write that down. So does this exist, limit, of f of x exist. And finally, we have to check that 1 and 2 are equal. So is it true that f of 2 is actually equal to the limit of the function at 2? These are the 3 points that we have to go through and check for our function. If any one of them fails, that means that our function is not continuous. If they all pass, it means that function is continuous at 2, and given with the fact that the separate pieces of it are continuous everywhere, it will mean that the function is also continuous everywhere. Okay, so f of 2, does it exist? Well, what happens if I try to plug in 2 into my function here? I have to look at the cases first. 2 belongs to this case right here because this is where equality occurs. So I would be plugging 2 into this expression and I will get that f of 2 is equal to 4. So yes, it's perfectly reasonable and this certainly exists. So I have passed my first check. Next up, I need to figure out whether the limit at 2 exists or not. And here, I know that the 2 is in fact my connection point. So I have a function that looks differently on the left than the function that it looks like on the right. So in order for me to find whether or not this limit exists, I need to find the limit on the left of 2 and the limit on the right of 2. If they are equal, then the limit at 2 will exist. So what happens as x approaches 2 from the left on my function? Well, if I approach 2 from the left, following along the function leads me to the linear piece. When x approaches 2 from the left, I am in the case that x is less than 2. So I will be computing the limit of the linear portion of the function. As opposed to when x approaches 2 from the right, I will be moving along the parabola piece because that's when x is greater than 2. So in the second case, I will be calculating the limit, apologies, this should be from the left, of the x squared. Now I can calculate each of these limits separately. So as before, the first rule of limits, plug it in. So I plug in 2 into here, 2 plus 2 is 4. There's no issues, it simply computes as 4. So my limit from the left of the function, from the left of 2 of the function is approaching 4. Here, same thing, plug it in, 2 squared is equal to 4. So the limit as 2 approaches from the right is also equal to 4. Since both of them exist and are the same, this implies that limit as x approaches 2 of the function also exists and is equal to 4. And finally, okay, so actually, I guess I can check this one off. So far, this property has passed. And now finally, I have to check that the function value that I found in part 1 and the limit value that I found in part 2 are indeed the same. Well, here, yes, we can see that the function value was equal to 4 and the limit value is equal to 4. So they're the same, and therefore my final check has also passed. Now I can conclude that since f of x is continuous at 2, and each of its pieces is continuous everywhere, each of its pieces, let's call them again by name, x plus 2 and x squared, is continuous everywhere, the function itself is therefore continuous everywhere. So thus, f of x is continuous at every single point. So continuous everywhere. Okay, let's take a look at another one of these. So here, because the example looks very similar, it does have a constant, but in spirit, it's the same justification as the previous example. I encourage you to pause the video and try this for yourself. Okay, so what do we have so far? So far we have two pieces. What looks like a line of some unidentified slope k, and what looks like a reciprocal function. And we're asked to find the values for k for which this function glued together is actually continuous. So let's again draw a picture to really understand what we have and what it is that we actually want in this case. So I have that my function is breaking into two separate pieces around 1. So let's say this is 1 here. Up until 1, when x is less than 1, it looks like 1 over x. So that means that here I have the full reciprocal function all the way up to 1. And I'm not including 1, it's not equal to 1 here. This is at height 1. And this piece is a line of, again, some unidentified slope k with the y-intercept of 3. So the y-intercept of 3 somewhere up there. But even without going into that much detail, all I can think about for now in terms of qualitative graph is that this is a line, okay? It's a line of some slope. So it's going to be a line coming out of here somewhere starting at 1. Okay, so this is some kind of kx plus 3 for x greater or equal than 1. Okay, so the real question is, can I find a slope k that somehow glues this line of mine to this point right here so that the graph carries on through a smooth connection point, right? Note that k could be different. The y-intercept is 3. So if we are to find something connects perfectly to this line, it's probably, to this hyperbola or reciprocal, it's probably going to be something that looks like this with the y-intercept of 3, right? But we can certainly try to find something where the k works out so that the two pieces glue together. But remember, the first step in my previous example was to determine where am I supposed to be looking for potential problematic points. And the first thing that I said in the last example was, because each of the pieces is continuous by themselves, my only concern is about point of the connection. Here, however, line is continuous, but 1 over x is not. There is an infinite jump at x equals 0. And no matter how well I glue this line to this connection point at 1, that is not going to remove my discontinuity at 0. So no matter how much I fiddle with k, this function is never going to be continuous at x equals 0. And therefore, we cannot actually find such a value where we can guarantee continuity everywhere. Okay, so let's record that. No values of k can remove discontinuity at 0. So we cannot find such values and make the function fully continuous. So this is a great lesson in thinking about thinking before starting to do quote-unquote math. It's very easy to get hung up on, oh, okay, I just have to do the arithmetic. So I just have to make sure that the limit from the left is equal to the limit from the right, set them to be equal, and find such k. Well, k isn't even the problem here. The problem is the infinite jump at x equals 0. So first of all, take a look at the graph and take a look at it from the sort of bird's eye view. Is there anything wrong with the pieces by themselves before you're trying to think about just the connection point? The connection point might not be the only culprit, and you first of all have to make sure that you deal with all the other ones. Okay, let's think about examples of continuous functions that actually occur in real life and whether or not they're truly continuous. So here's some descriptive examples of, let's say, natural phenomenon. The temperature in the room as a function of time. So in the room I'm in, it's end of August, it's getting warmer and warmer and warmer as the day goes on. Is it doing so in a continuous or discontinuous manner? Can the temperature just jump from, let's say, 23 degrees Celsius to 26 degrees Celsius instantaneously without having to go through all the values between 23 and 26? Well, no, of course not. So the temperature changes are going to be continuous. The weight of a woman from the start of her pregnancy to the birth of her child. Well, the birth of her child means that at one point in time, she will lose quite a bit of weight quite quickly. So this really depends on what your scale of time is. If, let's say, we are taking the intervals of her weight at 5 minutes apart. So let's write that down at 5-minute intervals. Then what we're going to see is that throughout her pregnancy, let's say this is time, versus weight. Throughout her pregnancy, she was gaining weight in some manner. I don't know if it was linear or if it was hill functioning or something like that. But if we're taking it at 5-minute intervals, then at the point of the birth of the child, the weight will drop within the 1 time interval and then, be somewhat stable. Okay, so there will be a finite jump here if the time interval is long enough. If we're taking it at like 1 second interval, then the function is still going to be continuous. But if we take it at far enough apart time intervals, then this will produce a discontinuous behavior. So this is another very important point to think about is what are your scales and how far apart are you measuring it? So I specifically did this in 2 different ways. If I measure the temperature in the room also at 5-minute intervals, then it will be a constant sort of step function, right? Whether it's increasing or decreasing or something like that, but there will be jumps. But by itself, as like measured, every millisecond, it will be continuous. Think through the rest of these by yourself and try to justify to yourself whether these are continuous or not and what types of assumptions are you making in order to justify whether a certain behavior is continuous or discontinuous. My last 2 examples here are actually going to be from the midterm from this class a couple of years ago. So this is the weight function to estimate the weight of a male broiler chicken during the first 56 days of its life. So what I have is between day 1 and 34, the weight is measured in a quadratic function. So the chicken is actually gaining weight quite a bit faster. Then afterwards, between days 34 and 56, it's beginning to look like a linear function. We could, of course, graph it and once again see on the graph whether or not it looks like it will be a continuous behavior and generally what it looks like. And I encourage you to do that. The coefficients here are so that I cannot produce a reasonable sketch by hand. Pull up Desmos by yourself and actually go through answering these 2 functions and seeing what they look like. But the question is it continuous or not? Explain why or why not. So the example is identical to the ones that we considered just a couple of slides ago. I have a piecewise function and I have to determine whether it's continuous or not. Now, because this particular function actually describes the weight of a living thing, I expect it to be continuous because again, if it's measured at every single instant, I don't expect the weight to be able to go from one value to another instantaneously. It actually will take some time, especially in things like growing animal, right? But I need to prove that this function, as constructed as a model, is in fact continuous. So pause here and try to go through this by yourself. It is identical to here I will flip back, to the actual steps that we have taken in this function here. The function itself is even identical in a sense of it's quadratic and linear. So there should be no surprises at all when it comes to what steps you should be taking for this particular question. Okay, so the first thing to say and the first potential mistake to make is to justify at which point you're going to apply those very specific analytic tools. We're going to first take a look at the functions by themselves. I have a quadratic function, so a parabola, a polynomial, and a linear function, a line, also a polynomial. By themselves, they are continuous. So the only point we need to check is the point of the connection. And that is a very important observation to include, because as we noticed a couple of slides back, the function not being continuous itself somewhere might be the actual problem. So first we have to justify that w of t is continuous for 1 to 34 and for 34 to 56 as it's quadratic and linear there. And therefore, we only need to check the point of connection. So the point of connection here is t equals 34. And there I go through my 3 checkpoints, right? The first checkpoint being the value of the function. Does it even exist? So w of 34. What am I going to do? If I plug in 34 here, I need to decide if I am in the first case or in the second case. And you can see that the 34 is included here, which means I will be plugging 34 in for t here. So W of 34 is 1.12 34 squared minus 0.56 times 34 plus 48.07. Okay, if you plug it in, you're going to get a number 1323.75. Okay, it's a valid number, so the function at that point indeed exists. Excellent. For my second point, I need to make sure that the limit as t approaches 34 actually exists. So in this case, and it will be the same for all of the piecewise functions, I can see that the function on the left and the function on the right are different, which means that I will have to check the limit as, not x, t approaches 34 from the left of my function, and the limit as t approaches 34 from the right of my function. Now, as t approaches 34 from the left, which branch of the function am I using, the first one or the second one? If I'm approaching 34 from the left, I'm coming toward 34, but I'm coming from the side being smaller than 34. So I am in this case right here, which means that I will be computing off with this piece of the function right here. So 1.12 t squared minus 0.56t plus 48.07. And again, first rule of limits, I'm just going to plug it in. And in fact, I've also just plugged it into here. So I know that this is going to be the same number in this case, 1323.75. Excellent. For my second limit, I am looking at t being approaching 34, but from the right-hand side, so being a little bit bigger than 34, which means that I'm utilizing this branch of the function. So I'll be computing the limit as t approaches 34 of minus 1022.25 plus 69t. Okay, again, first rule of limits, plug it in, and there's nothing here that will create any kinds of problems because it's simply a line. So I plug 34 in for t, and I will notice that indeed it's actually going to give me the same number, 1323.75. So these guys are the same, the one-sided limits are the same, which will imply that the limit as t goes to 34 of my function exists and is equal to that common value, 1323.75. There we go, squished it in. And then finally, for part 3, I have to make sure that my function value from part 1 is equal to my limit value from part 2, which of course is the case here. So I have that w of 34 is equal to the limit as t approaches 34 of w of t. Perfect. So they in fact meet at that point, which means that I can now draw my final conclusion here, which is that therefore w of t is continuous everywhere. Okay, so let's go through the steps again. There's a couple of very specific points. First of all, you have to justify why the point you're checking is the only point you are checking. So this is a key step. You are saying here that the pieces by themselves are perfectly continuous, so the only concern is the point of connection. And the rest of the problem, the rest of these 3 steps, is actually checking to make sure that that point of connection indeed connects the parabola graph and the linear graph of your function growth. Okay, so both of the steps are important in this case. Do not skip the first one because it seems trivial and obvious. Skipping it will sometimes cause big issues. Next up, we have the exact same question, but now it's asking whether the function is differentiable or not. So let's go back to the slide where we described all the possibilities for differentiable versus non-differentiable options and see what exactly we might be looking out for. Here is from earlier in this lecture, we have that for the derivative to exist, the limit that defines the derivative has to exist, which gives us that in all the possible cases, if the function is not continuous, it is also not going to be differentiable. But we're also acquiring an additional case of a cusp, where the function is continuous, but we cannot draw a unique tangent line at that point. So in order to determine whether the function is differentiable or not, we need to determine if any of these cases for it are true. If the function is continuous, and in terms of our broiler chickens example, it is, as we just discovered on the previous slide, that means that all of these cases are immediately eliminated. It's continuous, so it certainly doesn't have one of these issues. So the only thing we have to check is to make sure that it does not have a cusp. So the slope coming toward the point of worry from the left and the slope coming toward that point from the right actually are the same value and won't be producing two different slopes of the tangent lines. So in summary, we already know that this function is continuous as per our previous calculations, and therefore we simply need to make sure that it's also differentiable at 34, that there's no cusp at 34 at the connection points. So if we want to sketch a little quick picture here, I already know some things about this function. I know that at 34, I'm going to go from a parabolic to a linear behavior. So this is a parabola, and this is a line. And I, in fact, even know the point of connection because we calculated it in the last slide. It's 1323.75, I think, right? So they certainly connect, but we start off as having a parabola, and we carry on having a line. I need to figure out whether their slopes here are the same, and so they connect smoothly, or there's going to be this jagged cusp-like edge. So that means that I need to look at the slope of a tangent line from 34 coming from the left, and the slope of the tangent line as 34 comes from the right. So that means that I need to compare the slope of this parabola at 34 to the slope of this line at 34. So let's write that down. Parabola's slope at t equals 34. And what is that equal to? Well, my definition of the derivative is the slope of my tangent line at that point. So 34 plus h minus w of 34 all over h. And I need to figure out whether or not it equals to the slope of the line past 34. So on the other side, I'm going to have the exact same type of expression, but now for my line. So I have that I want to know if this is the limit as h goes to 0 of 34 plus h minus 34 all over h, except for my w here will be coming from the parabola side, so it will be this function here, and my w here will be the line coming from this portion of the function, so this function here. Okay, so despite the formulas looking exactly the same, my w pieces are going to be, in fact, different, right? And so what I have on the right-hand side here is line's slope at 34. So now I'm going to skip long and tedious calculations of plugging in the correct W for each case and calculating what these limits are going to be. So I'm going to say dot, dot, dot. And in fact, it's dot, 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 dot. It's quite a bit. But what is going to end up is on the left-hand side, you should get 75.6. And on the right-hand side, you should get 69. Now, of course, these two numbers are not equal. That means that the slope coming from the left is steeper at 75 than the slope coming from the right at 69. They're not the same, which means that the two tangent lines are not the same, which means that I cannot draw a single unique tangent line at that point, and therefore the function is not differentiable at 34. Since the slopes are not equal, the function is not differentiable at 34. Notice that, so the function, I'm going to say w of t is not differentiable at 34. So as I just started saying, notice that I have to be specific that it's not differentiable at 34. It is in fact differentiable everywhere else. The parabola will have a unique and existing tangent line at any point. The line will have a unique and existing tangent line at any point. So it is only at 34 that I cannot draw a unique tangent line, and therefore it's only at that point that my function is in fact not differentiable. Let's think generally now in terms of these tangent lines and what their behavior can actually tell us about the function. So throughout the pandemic, we have seen lots of different graphs of COVID-19 spread and then the actual spread, let's call it, of the vaccinations and the different waves and so on and so forth. So here's, for example, the graph of the COVID-19 cases in New York right at the beginning of the pandemic, so the first month, where we see that the cases are essentially increasing with some sort of small decreases occurring here and there, and it's not clear whether the decreases occur due to the bad collection of data or due to the fact that the disease somehow actually started getting a little bit more contained. Towards the end here, it looks like we're in a bit of a containment stage, whereas these intermediate steps are not necessarily indicative of that. The question is, if this is my function f of x that describes something, for what values c is what we're going to call them, is the derivative going to be positive? Again, remember that if you're given a graph, there is nothing you can do algebraically. So here we will have to interpret everything from a graph. So let's recall that the derivative at a point from the graph is a slope. So at a point is a slope of tangent line at that point. So when it's asking us whether the derivative is positive or negative, we're simply being asked, is the slope of the tangent line positive or negative? So let's record that as well. If the derivative is to be positive, that means that my slope has to be positive. So slope of tangent line is positive. Now, where does that happen on the graph, for example? And what might that indicate? So if I am to draw tangent lines to this graph at different points in time, some of them will be pointing up, some of them will be pointing down. If the slope is to be positive, it means that my slope has to look up, okay? The grade sort of has to go up. And that means that if the slope is positive, the function itself must have been increasing. The shape has to be pointing upwards. Right? So the conclusion to this is the function is increasing. And this happens in quite a few spaces, right? So for example, anywhere here, the slope is positive. So this is, the derivative is positive. The slope, for example, here is also positive. And we're seeing that, again, as long as the slope is positive, the derivative is positive, that immediately means that the function at that point is itself increasing. Now, it's only at that particular point where I'm actually drawing this tangent line, right? So I should be a little bit more careful too to indicate that I'm actually drawing tangent lines at particular points. If the derivative is negative, I'm actually going to copy this entire expression because all I have to do is think about the small changes to make in the exact opposite direction of all of my justifications. So if the slope is negative, what would that look like on the graph? Okay, if the slope is negative, generally the function, the line, will look like this. So if the derivative is negative, the slope of the tangent line is also going to be negative, and that would mean that the function itself is in fact decreasing. So this happens also at a few points on the graph, right? So for example, here, the derivative is negative, somewhere like here, the slope is pointing down, so the derivative is negative again, and so on and so forth. Positive derivative corresponds to positive slope of a tangent line. And we're very familiar with lines. Positive slope of a line means it's looking up, and therefore the function is increasing. If the derivative is negative, derivative being the slope of a tangent line means that the slope of a tangent line is negative, which again means in terms of lines that the behavior is looking downwards, so the function at that point itself is decreasing. And this, in fact, is an extremely useful and powerful observation because we are now able to connect the derivative behavior with the function's behavior. And this is something that we're going to exploit in quite a bit of detail later in the course.